So the material I want to present today is all about specifying and estimating discrete choice dynamic programming models and using them for purposes of policy evaluation. It's not really focused on inequality, although these types of models are often used to study questions related to inequality. So at the end, hopefully we'll be able to look at some applications. It's based mainly on this handbook of labor economics chapters that I wrote with Keane and Wolpin and Keane, which came out in the last handbook. And these, we call them DCDP models, have been, over the last 25 years, there have been a lot of new developments in many different fields, so labor economics, IO, demography, health economics, development economics, political economy. At first, the models analyzed relatively simple questions, mainly for computational reasons, but as computers have gotten a lot better, we're now able to study much richer questions. Okay, these are some of the earliest applications, like the very first ones. You can see in the early 80s, that's when they came out. So Gox and McCall, they just considered the decision of whether to stay in the military or to leave. So most of the early applications were just one decision, but it's over time. Miller considered the decision whether to stay in your given occupation or whether to change occupation. Pecos, so a lot of these papers are pretty famous papers now. Pecos looked at the decision whether to renew a patent. John Rusk had this paper where he looked at the decision about whether to replace a bus engine. And Keane and Wolpin had a model of fertility, and where the decision was whether you have another child. And that was estimated with Malaysian data, so an important feature in that data was the mortality of children and whether people try to replace children that have died. They have pretty high infant mortality. But these were the very earliest applications of these types of models. And we'll first start with some static frameworks and then look at how the static framework can be extended to the dynamic framework and how it carries over, say, for specifying a likelihood equation and estimating the likelihood. All right, so in terms of notation, it is a little bit notationally dense for this early in the morning, you'll see. So try and drink a lot of coffee. So DIT is going to denote the decision a person makes at time I, or person I at time t. And we'll look at decisions like related to labor force participation and later on related to fertility. And in the binary, the first just looked to consider a binary static framework where people are making some decisions. And usually what we do in the binary framework is set it up as a threshold crossing model with a latent variable. So V star is the latent variable here. Okay, and then people make the decision that gives them the largest payoff. So the V here is going to be the difference in utilities from making one decision versus another decision. Like this is like the standard random utility model that I'm sure in probably in first year or second year econometrics you encountered. Okay, and this latent variable V could be a function of different types of variables. So one is that it could depend on past choices. Right? So whether you worked yesterday could have an effect on whether you work today, for example. It could be a function just of some additional X variables. You know, so these might just be some features of the environment over which the person doesn't really have any power, so they're not making decisions. Or it could even be just like their education level, demographic factors. And then it can also depend on some shocks. And those shocks are usually like preference shocks, wage shocks. You know, but there's some things that are unobservable. Okay, and everything has a T subscript. So in these types of models, the information is gradually realized, right? So you don't see the shock until you get to that period, and then that shock is realized, right? So some information is gradually revealed. Okay, and so we can write the decision rule here that D is a function of these variables. And pretty much all binary choice type models can be written as some version of this type of threshold cross model. And the model is dynamic if either past decisions enter here, or say these unobservables are serially correlated. Because then if they're serially correlated, then the unobservables today are going to affect your predictions of the unobservables tomorrow. Okay. And then why might we want to use this type of model? Right? So usually there are different goals people have when they're doing some analysis. So one is you might want to test some prediction of a theory. Right? That's a common goal in empirical work. That you have some theoretical prediction, you want to test it with your model. You might want to determine the impact of a change in D or X on choices. Like for example, suppose D were the decision to attend school. And then you could say, well, what if we forced everybody to finish high school? How would that affect their future lifetime trajectory? So that would be like the impact of a change in a decision variable on choices. Or there may be something else, like a change that's not in D or X. And the example that we'll look at is a subsidy. Say a child care subsidy, something that affects the budget constraint. It's not directly a choice or anything, but we may be interested in looking at policies that influence other aspects of the model. So there are different types of decisions, or different types of questions we might be interested in. Okay, so this is, now we'll just start with a static model and then extend it to the dynamic framework. And in the static model, we're going to assume that there's some couple making the decision about women's labor supply. So this is just like a unitary model because there's just one utility function. And they get utility out of consumption, so it's like household consumption. DIT is whether the wife works. And then these are some other observables that could affect her utility from leisure. So typically, we would say how many young children she has affects whether or not she stays home. Right? It's not really leisure, but we call it leisure. So anything that involves the wife staying home is leisure here. So her utility from leisure is affected by some other observables. And that could also include like wife's education. And then these epsilons are shocks. And the reason they're written in this way, it's really just a function of epsilon, but this is just to say that they're leisure shocks. So it affects her utility from leisure. So usually in these models, you have to have as many shocks as you have choice variables. So we'll talk about that later, but when you specify the likelihood to not have a degenerate likelihood, you need to have shocks that correspond roughly to the number of choice variables. Okay, so that's the setup. And then, so we'll assume standard assumptions on the utility function. And then we'll assume for now that the unobservables, so the preference shocks, those are the epsilons, are drawn independently over time at first, and then we'll look at how you can relax that assumption. So marginal utility of consumption is increasing, diminishing marginal utility of consumption, and you get more utility with leisure than without. And in this model, the wife is going to get a wage offer in each period. And if she decides to work, she incurs a child care cost. And then we can use this type of model to analyze policies related to, say, subsidizing child care. Right? That's a policy that, even in the US, they have a lot of programs that subsidize child care. But many countries have programs that affect the price of child care. Okay, and this Y is just husband's income. So the husband is just contributing income to a household, and we'll just assume the husband always works, even though the model could easily be extended. And so it's just kind of keeping it simple for illustration. Okay, so if she works, she gets a wage W, But she has to pay a childcare cost, which is multiplied by the number of children she has. So NIT is the number of children. And we'll start off with number of children just being exogenous, but then later on show how we can relax that and actually incorporate fertility choices into the model. Okay, so wage offers you don't observe for women who are not working, and so therefore you need to also specify a wage offer equation. So wages are going to depend on some Z's and then also some unobservables. Okay. Like a common specification is to allow wages to depend on work experience. You know, and oftentimes when people don't have data on actual experience, they use what's called Mincer experience, which is age minus education minus sex. But later we'll actually look at how you can incorporate actual experience into the model into a dynamic version. But right now this is just static. Okay. And so we'll also assume wage shocks are just IID. And then we could make some distributional assumption on the unobservable factors, that they have some joint distribution. You know, typically normality, that you can assume kind of whatever you want. Okay, so this then leads us to the utility under the two different choices, right? If you choose to work, you get this utility, you get your husband's wage, plus you get your wage. I mean, actually, it's a joint decision. It's a household decision. But you get the man's wage, the woman's wage, but you incur the child care costs, and then the woman doesn't have any, you know, utility from leisure. You know, but those are the two different utilities associated with the two choices. Okay. And so that's the latent variable function, right? Just the difference in utilities, and you participate if that's greater than or equal to 0. So these are all observable things, and these are some unobservables. But we're always assuming in these models that the people see the unobservables. Like at time t, they would see all the unobservables up till t. But we, as the econometrician, do not see the unobservables. Okay, so the state space for the household is everything, including stuff that we don't see. But then you can write this, so omega is going to be the state space. The state space with this little minus sign is all the observable elements. So those are the things that we see and we can use in our analysis. And so we can define the set S. Those are the set of unobservables that induce a person to choose to work. Those are all the different draws of unobservables that would lead to a working decision. And then, like, given this notation, you can write down the probability that we observe a woman choosing the working option is just going to integrate over the set of unobservables that would lead to working. And that's then the G. We can call that G. This is just a probability that she works. And then probability she doesn't work is 1 minus that. Okay, so G, you can see, depends on, since we're integrating out over the unobserved things, right? G only depends on the observables. And it's a function of different elements within this model. The utility function, the wage offer equation, and the distribution of the unobservables, right? All those things enter into G. Okay, so structural estimation. So this slide actually is just considering different approaches to estimation, right? Structural estimation is usually concerned with recovering what are called structural elements of the model. So structural elements of the model are like the utility function, the wage offer equation, or the F. Those are all structural elements of the model. So if you wanted to estimate this model structurally, there are actually a couple different ways people use the term structural estimation. Like this is one definition that it refers to the structural elements like these utility function, production function. Some people also use it to mean anything that's policy invariant, which is a little more of a relaxed definition. So you might see it in that context. The structural elements are policy invariant, but you could also have other functions that are policy invariant that are not the structural elements. But just to be aware that there are a couple different ways people make these distinctions. So non-structural estimation would usually just be concerned with recovering G, the probability directly, and not trying to separate out these different elements, like F or U or W. And then you may or may not adopt functional forms. Like you could have, so these are different approaches. So you could have a non-parametric, non-structural approach, where you try to recover the G without it making functional form assumptions. Or you could have a parametric, non-structural approach. Say you assume normality, but you don't try to uncover the utility function or anything. You just try to recover the G. Or you could have a non-parametric structural. So that's more unusual. Like I have a little bit of work trying to do this, but you don't see a lot of examples of non-parametric structural. Or you could have, oh, this should be structural. I just see typos here, right? Or parametric structural. So we'll look at what do you get out of these things. Considering 3 different goals, and what you need under these different approaches to analyze these types of questions. So suppose we wanted to test the model by testing whether the probability of working is increasing in the wage offer. That's one implication of the model. So we'll look at how you could do something like that. Or you could just look at the impact of changing any of the variables in the model, like some of the x's or the kappas or something on the participation probability. And remember, I said that you might be interested in childcare subsidy. So that's not an X, it's not a D, but it's some environment. So the childcare subsidy affects the budget constraint. You might be interested in how that changes the probability of working. Okay, so non-parametric structural, you could estimate this non-parametrically, right? So that would be, so how would you do this non-parametrically? Any ideas? What's your favorite non-parametric estimation? Yeah, like kernel regression, yeah. So you could just do kernel regression, or there's all different ones like spline regression or local regression, local polynomial regression, or neural networks or wavelets. So there are many different methods, right? The main challenge is if you have too many variables, the convergence rates can be slow. But in principle, if you had a large data set, you could estimate those relationships completely non-parametrically, right? And so to test whether the probability of work is increasing in the wage offer, you need to be able to vary the wage offer independently of other variables in the model, right? And so the things, the Z's are the variables that enter the wage offer. So you can see that you need to have some variables in Z that are not in kappa, right? Because you need to be able to look at how does G change when we change something that only affects the wage offer. So you need what we call an exclusion restriction, that there has to be some variable in Z that's not in kappa, and also not N. N is number of children, so that shouldn't really affect the wage offer. But if Z and kappa perfectly overlap, then you could not vary the wage offer, independently. So what kind of variable would you put in Z that, say, maybe is not in kappa?
Can you remind me what kappa?
Kappa is like all the observables that affect utility of leisure. affects, and something about the environment that affects the wage would work, yeah. Like even in this work experience, if that didn't directly enter into the utility function, you could use work experience as something that affects the wage. So, but you need some exclusion restriction. If you observed wages for everybody, then you wouldn't need an exclusion restriction, because then you just put wages in directly. But because you don't observe wages for everybody, you need an exclusion restriction. Okay, so the second goal, that's just looking at the effect of any variable on G. Well, if you do that relationship non-parametrically, you can look at the effect of any variable, say, of n, changing n on G, but you are restricted that you can only do it within the range of your data. Right? Because any non-parametric estimate, you can't extrapolate, right? Outside your data. So if you only observe people who have up to 5 kids, you could not say what would be the effect of having 9 kids. Right? That you can do non-parametrically. And then it's not possible within this model to identify the effect of a change in the child care subsidy. Okay? And that's because in the data, we're assuming that you don't see the subsidy, and it's not, there's no variation in the data for you to see. There's no pi here. You don't see pi. It's not like pi varies in the data. So if you want to say what is the effect of subsidizing childcare, you couldn't do it within this non-parametric, non-structural approach. All right. So now parametric, non-structural. Then we would just choose a functional form for G.
What could you do in the non-parametric, non-structural model that has policy relevance?
Oh, you didn't like goals 1 and 2? Well, I mean, you can do any of the things that would vary, like n or kappa. But you can't do things that like change the budget constraints. If you observe data on childcare subsidies, then you could, because then you could estimate G as a function of the childcare subsidy. Yeah.
What if you have observed the price of the childcare without subsidy, but I mean you know exactly the price that they pay now?
Yeah, if you observe the price people were paying, then you couldn't do the effect of subsidies, because that would be analogous to changing the price. Okay, so parametric non-structural, that's just choosing a functional form for G. And so you can basically do the same things as with the non-parametric. You still need an exclusion restriction. The only, one difference is that you can determine the effect of changing the variables even outside the range of the data. I mean, it may still not be a good idea, but you could say, if you estimate the effect of number of children on women's labor supply, you could say, well, what if she had 10 children? Even if there was nobody in your data like that, you could actually do that because the parametric assumptions are going to let you extrapolate outside the range of your data. Okay, but otherwise, you still can't do, say, the effect of a child care subsidy without direct price variation in your data. Okay, non-parametric structural. So usually, you can't recover the utility function, the wage equation, the joint distribution, the errors non-parametrically. It's usually not feasible to try to recover all those things. Hopefully, we'll have a little bit of time that I could show you some of the results on what we've been working on, trying to do some things non-parametrically and structurally. But it's not possible to fully recover the structural elements from the model non-parametrically. Okay, now let's look at parametric structural, and it turns out, like within this context, we can also do the childcare subsidy experiment. Like even if we have no data, direct price variation on price of paid for child.
Petra, with that last comment you made, when you say it's not feasible to fully non-parametrically recover all those things, is that a statement about identification, or is that a statement about working within the constraints of a finite sample?
No, it's identification. Like
It's
it wouldn't be possible to separate out like utility without making any assumptions on the functional form. Yeah.
So like, you know, aside from like simple things like, I don't know, concavity or things like that, you know, if you impose maybe not specific functional forms, but you know, assumptions on certain, you know, aspects of them.
Yeah, I think you could probably, with some restriction, I mean, like Rosa Mexican has a lot of work in looking at, you know, what can you recover and what types of, are the minimal assumptions needed, like concavity or, but you couldn't get all these things for sure.
Okay.
Yeah. So now let's look at an example of how we would do this parametrically, structurally, and then how we would do this childcare subsidy experiment, even without data on the price of childcare. So under this approach, you have to specify a utility equation. You know, so here utility, this is just very simple, linear in consumption, and then this is utility of leisure, the alpha. And remember that we want to have a shock to preferences for leisure. So here, this is saying the alpha depends on some observables plus some unobservables. Then this is just the budget constraint that we had before. And then we parametrically specify the wage offer equation. And then also parametrically specify the joint distribution of errors, that it's normal. Okay. So now the difference in utilities, we can write this way. So these are the unobservables added together, and this is this observable part, which is a function of the observed elements of the state space. Okay, I mean, it turns out you don't need additive errors, but just for this simple example, I have additive errors. I mean, actually, you wouldn't normally have additive errors, because usually when people write wage equations, this is log wage rather than wage, and so then you don't have that, you know, the simple, but it's just to keep the notation simpler, but it's not required that it be additive. That's the restriction.
Can I ask, just because you said earlier that you want the same number of errors as you have choices? And so by that, do you mean there's a zero, is a 0, 1 choice, so there's 2 choices, and you consider that 1 choice, and are there 2 errors here, or is this because they're added and we can think of them as 1? Or did you mean at least as many choices as you have, at least as many errors as you have choices?
Yeah, so there are 2 errors here in the model. There's the wage offer equation, and then they add together, so essentially then there's just one error. Although you can actually recover, because you see wages partially,
okay,
you know, you can actually recover the parameters of the joint distribution. So the reason you need as many errors as choices within these models, you have to explain why people who are observably identical possibly make different choices. Because in your data, you're going to see women that have husbands that earn the same amount, and they have the same number of kids, and they have the same education level, so they're observably identical people, and one woman's working and one's not. So that's what the preference shock will explain.
Yeah, I think I misheard you earlier, so as many errors as you have choices.
Yeah.
So it could be 1.
Yeah, so kind of, it depends on the model, like where you put in the errors, but we're trying to explain women's working, so that's why it makes sense that the error affects the marginal utility of leisure. Like you wouldn't put the marginal utility of fertility or something if your model's not about fertility, you know, so it has to be related to the choice that you're modeling. And if your model cannot explain that two identical people make different choices, then that's called degeneracy, right? Because the probability of observing that is 0 on your model, because your model can't explain it. So then we say it has a degenerate likelihood, because it can't explain something that's in the data. Okay, and so actually look, husband income difference is out under the specification we have, because it affected the utility of working and non-working the same way. So it actually doesn't affect participation. And then here's the likelihood function, so in terms of how we would then estimate the parameters of this model. So for women who work, we see their wage and we see that they're working. So the likelihood has to incorporate both of those things. And then for women who don't work, all we know is they're not working. So that's the only part of likelihood we have. So the probability that you work is going to be the probability that your preference shock would, so that's those two added together, right, the psi. Probability that this is greater than some threshold. Because there's going to be some threshold for each, element of the state space. The observable elements, there's going to be some threshold where everybody above the threshold chooses working and everybody below doesn't. But that would be the specification of the likelihood in a static model. Right? This is very close to what you've probably already seen, like in Amemia, if you work through this chapter on COVID models. You have 5 different types of COVID models there. And this is one of the COVID types in the text, Econometric text. So that's a very good chapter if you haven't had to look at it yet. So these are the parameters that we want to estimate. Right, beta, these are all the parameters from the model.
Sorry, what was the name of the book you mentioned?
Amemia, it's Takashi Amemia. It's called Advanced Econometrics. It was a very popular textbook when I was in grad school, but he had a very nice presentation.
We've just been dated.
Oh, nobody looks at this book anymore. Yeah, he had a very good discussion of COVID models and duration analysis.
In the specification of the parameter in the utility function, basically they are a function of observable and unobservable characteristics. Is there a trade-off on the number of observable characteristics that you can use to specify this parameterization?
Yeah, there's a trade-off computationally because, well, especially in dynamic models, the size of the state space affects how long it takes to estimate them. Because there are a lot of things, you can see here even that you have, the threshold differs for different observable elements of the state space. Right, so the bigger your state space, the harder these models. And it's more just computational, it's not, hypothetically, it's easy to think about bigger state spaces and not even hard to write down models with bigger, more things entering, but it's just computationally it gets harder. But we'll look at some methods you can use to approximate there are approximation methods when your state space is large.
And on the other hand, you cannot use only unobservable because otherwise you are too much.
Oh, too many shocks has a different problem. Like that has a problem that you have to solve these numerical intervals. Then if you have like 5 or 6 normal shocks, then it gets just difficult to solve numerical intervals. And usually we do it using simulation methods, and then you need a huge number of simulations to get something accurate. So there is a balance between how many unobservables and how many observables. And that's the main limit to how many choices we can consider, is that it just gets computationally hard. Okay, so in terms of the wage parameters, we can just use standard, Heckman, this is like a Heckman 2-step in terms of estimating the wage equation. So normality is sufficient to identify the wage parameters, and then you'd also get this, just from the regression, if you did the Mills ratio correction and everything, you would get those things. if you did just a probit model for whether you work or not, you see that you would identify, well, let's just remind ourselves what these gamuts were. But this was on the wage equation, and this is on the utility from leisure, right? So you can get these two things. If kappa and z totally overlapped, then you could not, that's if you had no exclusion restriction, then you wouldn't be able to separate those, right? So here you'll also need an exclusion restriction. So let's see. Here you also estimate the child care cost. Let's see if you can see that. So as part of this estimation, we'll get an estimate of this pi. Right. From the probit model, you would just get pi divided by this error, right? But then this error you can separately identify because from the wage equation, you get this gamma. The wage equation comes down the scale. And then, so if you have one exclusion restriction, so in the wage equation you get gamma. From the probit for whether you work, you get gamma over the sigma psi. And so if you have one exclusion restriction, so there's one variable in z that's not in kappa, then you get the sigma psi, right? And then once you have that, one of these is going to be pi over sigma psi, and once you have that, you get pi. So the exclusion restriction is important to being able to estimate pi directly, because it's important to get the sigma. And you'll see, I think, the next slide, why sigma is very important to do policy analysis. Okay. Yeah, so variables that only appear in z, variables only in kappa, variables that are in both. So, this is what I was just trying to say. I forgot I had a slide on it. So having identified the wage function parameters, which are the gammas, to get the sigma requires one variable that's only in the wage equation. So that's the exclusion restriction. Okay. Now let's look at how we use this model for these different goals. Okay, so the first goal, so within this model, since everything's parametric, you can extrapolate outside the range of the data. And then let's see, the third, this was something that you couldn't do with the other approaches. So let's see how we can do it here with this approach. So suppose you want to implement a child care subsidy where the couple gets a subsidy tau if the wife works. Okay, so this is how her budget constraint would change with the subsidy. Right now, instead of paying pi, she gets to pay pi minus tau for her child care. Right? You can make it free even if you wanted to. Now you can write down the probability that the woman works within this model is going to be this here. Right? That's the probability. And if you estimated all these things, right? So from doing the likelihood estimation, you have gamma over psi, you have beta over psi, you have all these things. Now you see how you need this psi in order to incorporate this here. But given one exclusion restriction, we have the sigma psi too, right? So if you have all these parameters, then you can actually estimate the probability that she works given this subsidy. For any value of the subsidy. So you could consider a whole range of hypothetical policies that the government might want to introduce. And you could predict what's the probability that women work for different amounts of the subsidy.
So when you're estimating the price of pi, price of childcare, is that interpreted as some sort of average price that everyone pays?
Yeah, right now it's just that everybody has the same price, but you could introduce like heterogeneity in pi. I mean, right now I'm assuming that there's nothing in the data about pi. Sometimes you actually have pie in the data to some extent. Yeah, so right now it's kind of just simple for the example.
Are we making an assumption about the relationship between the leisure shock and the number of children she has?
No, well, it's independent.
It's independent.
Yeah, that all the shocks are independent when we write down this normal. And so a richer model, which actually later on in the slides is a richer model, where she also chooses fertility, and then there's a fertility shock, and then those shocks can be correlated. So you don't have to have independence. Right now the N is just exogenous, and so therefore it's independent. Okay. And so you can predict the effect of different policies for a range of subsidies. You can also predict how much the government would have to spend for different policies, right? Because just the number of women who take up the subsidy, you'll have a forecast of that with the model, right? And so therefore you can predict the cost to the government of different types of programs. Right, so you can do things like within this kind of model that you couldn't do non-structurally. Right? So it kind of depends, whether you use these types of models or not, depends in part on what your questions are. Like what types of questions do you want to answer? You know, but here we have like a program. We'd like to forecast the effect of a subsidy program, even though in the data there is no program. You know, so it's like introducing a new program that you don't even see in the data. And the reason we can do that here is that the child care cost is isomorphic to a tax on the wage. You know, so you can see it in the same way that if a woman works, there's a change in child care cost, and that's the same as, like a decreasing the child care cost is the same as increasing her wage. You know, and through the model, it comes out that way through the budget constraint. You know, so that's how we're able to do this policy, even though there's no data on costs of childcare at all. But it's just using the structure of the model, you can see that it's analogous to changing the wage. Okay. So the exclusion restriction, that's important regardless of whether it's structural or non-structural. You know, so within a lot of these models, it's really important to have exclusion restrictions for identification of certain parameters. Let's see. Yeah, so there is. So the child care cost change, there is some work, there are only a couple papers, but Ishimura and Tabor had a paper, and then I have another paper with Ken, where we try to do these types of goals using a structural model, but not making functional form assumptions. So you don't recover the elements of the model, but there are certain types of questions you can actually analyze without having to impose functional form, like without normality. So we might have time to look at some examples of that. Okay, parametric, one advantage is you get to extrapolate outside the range of the sample, you know, which you may or may not like, you know. I think it's a bit dangerous sometimes if you don't pay attention to where your data is. You can go way outside the sample and it may not be very reliable. Okay, and then the main advantage of imposing more structure is you can do, you know, different types of policies that you couldn't do without imposing the structure. Okay, so now let's look at dynamic models, and we'll consider a similar model and then look at how the estimation of this type of model can be extended to dynamic frameworks.
Petra, sorry, before you move on, do you mind if I ask a question about what you just talked about? So when you do the policy counterfactuals about, say, a child care subsidy, you didn't say anything about how the subsidy is financed, and I'm just kind of wondering if these structural models like take into account, you know, how do you finance it with the tax on wages? Because that's going to introduce like some weird equilibrium results, because you might incentivize people to have more kids, for example, if you're going to subsidize, like if you're going to pay for it.
Yeah. So the model that we were just looking at it as like a partial equilibrium model. So it doesn't have, you could, within this model, introduce how they're financing. So you could say there's some government budget constraint that you could add to the model, and that they're financing this childcare program with a tax on wages. And then you'd actually have to simulate to come up with the correct tax on wages to be able to, because that has to equal, the outlays on the program have to equal the amount raised through taxes. And you'd have to take a stand on who are they taxing, because people have different wages. But you could incorporate all those things. And a lot of the recent work on estimating these dynamic discrete choice models tries to incorporate. So that still wouldn't be general equilibrium. If you wanted to have like disincentives on, so you were concerned about like fertility, incentives for fertility. Oh, that would be easy to incorporate just by making fertility a choice. Then we would get that even without anything else. You could. So later on, I have some slides where fertility is a choice. So even without the government budget constraint, you could get incentives for fertility.
Yeah, I was just kind of generally wondering, because I feel like when you do the counterfactual analysis, it will depend on how you finance that, right? Like your conclusion that you draw about like what the equilibrium, outcomes are.
Yeah, but you can add that for sure to these models. Like you could impose a tax, used to finance the childcare costs, like a tax on wages. Yeah.
Can I ask a question that I don't think is I think I probably should be able to figure this out, but I hope you can help me with it. So when you think of the subsidy as simply being isomorphic to a change in the wage, it makes me think, oh, well, I can see changes in wages without doing a structure. I mean, I actually observed changes in wages, and so couldn't I just say, oh, well, in my non-structural model, I just looked at 10% more wages, right? Mm-hmm. I think that there's a problem with that, but I can't pin down what it is.
Well, you don't observe wages for everybody.
You don't observe
wages for workers.
Okay.
So if you had the wage offers for women who were not working,
then you would be able to do that without a structural. You would be able to do that non-structurally.
Mm-hmm.
Is that the only?
Well, I mean, you need to structure the model to know that it's analogous to change in the wage. Like if you didn't have the model at all, you wouldn't even have anything to tell you that it's analogous to change in the wage. Like you need some model. You may not have to estimate the model, but you do need some sort of underlying model to tell you that I should think of this as a change in the wage. Because you need a budget constraint even to think of it that way.
So it's nothing to do with the unobserved. Well, it is something to do with the unobserved shocks to leisure, because those are what give us the ability to get the wage offers for those we don't actually observe. Okay. But it relates to that only because through that non-observed offers.
Yeah, I mean, that's an important complication. But if you only estimate this G function and you never write down what's the budget constraint, then you wouldn't even know to think of it like a change in the wage. So I mean, you could estimate. You can write down a model and say this is the model that's motivating my empirical work, and then still do it non-structurally. But otherwise, if you just only did it non-structurally without any model at all, you wouldn't really know how to relate this to change in the wage. Okay, so this is now just extending that framework to a dynamic model, and I wanted to just show that the dynamic models are very similar to the static models, that there's not a lot of complications introduced by the dynamics. And so the way we'll extend to dynamics is just to add that the wage depends on your work experience. And your work experience is a function of your past work decisions. So when you decide today, do I work or not, you take into account that if I work today, that'll give me higher experience tomorrow. And so therefore, you have these dynamic considerations that we didn't have before. Okay, so that's what H is, the sum of your past working decisions. So work experience evolves over time with your D. So every time you work, you get one additional year experience. And then we'll assume still that the preference shocks are serially independent, and then that they're joint normal. But we'll look at how you can relax some of these assumptions later. So the couple is maximizing their expected present discounted value of lifetime utility in every period. And in these models, the shocks are gradually revealed to them over time, right? So at time t, you see the shocks at time t, but you don't know the future shocks. Okay, and just to keep things simple, we'll just assume the wife retires at some t, because everything I'm doing today is finite horizon. I mean, you could also do infinite horizon models. It's just I happen to do lots of finite horizon models. So the slides are, the estimation approaches and everything are going to be for finite horizon. Okay, so here's this is with the value function, the present discounted value at time t of remaining lifetime utility, and you're just choosing D, you know, which utility you get, the working utility or not. And then we can write this, and the way these models are solved is as a Bellman equation. So it's useful to write them in Bellman equation form. So this is the value function associated with choice K. So that's going to be current period utility plus the discount. So this is new because we have a discount factor here that we didn't have before, right, in the dynamic model. So that's one additional parameter. And then this is, now this expectation, the things that are unknown are shocks. The individual is gradually having their shocks revealed. So that expectation is over all the unknown elements of the model. So all the random components of the state space in the next time period.
So, how does it work without a simplified design?
Yeah, I mean, I've only worked in like one project where we had infinite horizon models. It just requires a different estimation approach. But for sure, it's not that much more complicated. It's just, I estimate a lot of models about people's life cycle, like individuals making decisions over their lifetime, and then at the end they die. And so it's kind of reasonable that for the work I do, like they're saving or whatever. But if you do like OLG type models, you know, then you normally have, you know, multiple generations overlapping, and then you have infinite horizon. So it depends what kinds of models.
And what method do you, how do you estimate it?
Well, there you have to solve that, like, there it is like a fixed point that you have to solve that the V's are equal. So it is quite a bit different, the estimation approach, than what I'm going to describe here. Okay, so in this case, the latent variable that determines whether people work or not, everything's the same, except now we have this additional term, which is the discount factor times the difference in the future expected value functions. Right? Because now when you decide to work today, you also take into account the effect on your future utility. Okay, but otherwise it's the same. And this is a function of the state space. You know, so it's just that this threshold psi is a different value because you also have to take this into account. Okay, so that's the only complication introduced, right? That you have this additional term here. Okay. So the full solution to the dynamic programming problem, we need to, in order to write down the likelihood, right? Remember, the likelihood is going to be a function of these cutoff values. And in order to get these cutoff values, we need to have these values, right? These expectations. And those are called Emaxes in this literature. And so we need to solve for all these things. So when we solve the dynamic programming problem, you know, if we had this, then you could just get the cutoff values, write down the likelihood, and there wouldn't be any problem. So the main complication is we have to solve now for these things. Okay, and those are called Emaxes. So let's look. So the solution method, the way it proceeds is by backwards recursion. Okay, and first we have to say something here about how some of the observable state variables evolve, like z, n, k, or kappa. So we could have like laws of motion or something for each of these things, but just to keep things simple, let's just assume they're constant. You know, so this would be like fertility or labor supply for older women that are not having changes in number of kids. So the only thing that epsilons are going to be varying. So, okay, I know this one looks a little bad. Okay, so we need to calculate these alternative specific value functions for each element of the state space. And that's to get these Emax T's, okay? So looking back here at this equation, we need the expectation of these errors conditional on working. And you work when this threshold is greater than or equal to 0, otherwise you don't work, right? So in order to get those expectations, that's what this is. So this is the expectation of the error term conditional on not working and conditional on working. So the Emax, you would take the expectation of that whole expression for the value function. So let's see, taking the expectation, not of this, well, it's the one with the utility function. I should probably reproduce it. But to get this, so this is this is current period utility, and we're taking the expectation, and then this is the, let's see. I mean, this requires a little bit of algebra to show this, actually, that it has this form. So it's not going to be easy to see immediately why this is. But this is just to solve for the Emax T. So in this simple model, since we only have one shock and we have we have two shocks, but the difference in the two shocks is normal. And so you actually get these expressions. Normally, it's not that simple. Like most of the models I estimate don't have one shock in the end. They usually have like 5 shocks. And so you don't have usually these closed form expressions. But in this simple model, because we've only got those 2 shocks, and we take the difference, so we have 1 shock, you can solve explicitly for this Emax. So in those papers from the 1980s, a lot of times they had 1 shock. So you see these types of expressions. But in most of the models that we estimate nowadays, it's not that simple. So you don't even have these closed forms. So, but this is not hard to do. You just have to take the expectation of the value function, and you get that. Okay. So you can see that you have these normal CDFs. So that's going to require some numerical integration because there's no closed form for that. You have a different value of the Emax for each state space, right? For each state space element. Okay, so this is now a value function at period. So in period T, the last period, there's no future, right? So there's no Emax in the last expression because you only have current utility because it's the last period. In period T minus 1, you get current utility plus the future Emax, right? For if you work or if you don't work. And so you need the Emax in period T minus 1. And then these models are solved backwards. So once you have period T minus 1, then we would do the same thing for period T minus 2, T minus 3, and so you get the Emaxes that way. Okay, so this is the latent variable for period T minus 1, whether you work in period T minus 1. So that's the difference in current period utilities And then this is the future Emaxes.
Can I ask a question? So since we're assuming a pretty simple structure of the problem, in this case, could we have like linear utility and everything? Could we have actually just solved for the what the functional form of the Emax is?
Well, that's what this is. This unfriendly expression is solving for the Emaxes. Yeah.
Okay.
So yes, you can. And the like they had.
That's what's letting us do it. Okay.
Yeah. I mean, these things still, there's no closed form, so you still have to do like a numerical integral to get normal PDF. But you do get this nice, simple. I know it doesn't look simple, but that is what that's doing. Just with some algebra, you can get to that. Yeah.
So if I'm rephrasing what you're saying, it's essentially that, pretend we don't have a whole lifetime of working. Pretend we're just like 3 periods, right? So in the last period, we have to solve this Emax. Basically, we're finding out what the probability of making each of these choices in period 3, given that we may have had 1 year or 2 years or 0 years of work experience at that point, given that the shocks we're going to get then. And then we're going to plug those different options back in to then say, okay, so this period I've had 0 or 1 years, and if I were to choose 2 or 3, or 0, 1, or 2, and if I was to choose 2 or 3, this is what the possible max is in the next, just very, okay, backwards recursion.
Yeah. Cool. And actually, the way you solving the model is totally separate from estimation. So it could be, like your model could be about 20 years of decisions, even though in the data you may only see people for 3 or 4 years. Yeah. Like that's totally separate. Because the models can extend beyond your data, even. Okay, but mainly the thing to take away is these models are usually solved backwards, starting with the last period when there's no future, and then that's the way you get the Emaxes. I think that was that actually kind of describes. But these are now the Emaxes going backwards for each period. And the latent variables for each period. And the reason we need this is because you need the cutoffs. Those cutoffs enter the likelihood. Okay, so you continue to solve backwards. The solution to the dynamic programming problem will be the Emax functions. And those are going to be inputs into the likelihood. Right? And so once you have the Emax functions, then you have all the ingredients to calculate the cutoff values that go into the likelihood equation. So we're assuming people have data on actual work experience to estimate this model. And so let's assume that you see couples over some time period, like some first period to the last period of observation. It doesn't have to be from the beginning of marriage. You may see people in the middle of their lifetime at different ages. Like you don't have to see people over the whole time period that they're making decisions, right? Okay, and then this is going to be then the likelihood. So likelihood, it's like the static model, but now we also have this product over the different time periods when you see the people, right? But other than that, everything is analogous. Right? So, and it's just that now this cutoff also incorporates the Emaxes into it. Right? That's the only difference.
So if you don't see people at towards the end or towards the beginning, are you kind of trading, or your functional form assumptions are essentially giving you what's going to happen there?
Yeah.
Okay.
Yeah. Because you're assuming it's kind of a stable utility function over time. It's not like a totally different utility function at each age. So even if you only see them over certain time periods, you're assuming that that's stable in other time periods, other than the discounting and everything. So you don't have to see them the whole time period. Yeah. In fact, I've seen Keane and Wolpin, they solve the model up to age 65, even though people in their data, I think, are in their low 30s, are the oldest people in their data. So it doesn't have to. It's probably slightly better if you have data that kind of covers the whole range, but it doesn't really have to for that information. Okay, but I'm hoping that you can see how the likelihood and everything is very analogous to the static framework, right? So it's not that there are a lot of complications, it's only that these cutoff values now incorporate the value functions, right? And in order to get these Emaxes that enter the cutoff, you have to solve the dynamic programming problem. You know, but once you do that, I mean, it's really like a two-step process. First you have some parameters you're considering, you solve the dynamic programming problem, you get all these Emaxes, and then you can form the likelihood. And the likelihood now we take into account what data you actually have. So this could be different ranges for different households, right? So this doesn't even, you don't have to see people for the same number of time periods even. I mean, there are some complications. I'll just tell you briefly, if you're missing data. Like suppose you saw households 1 year, then you're missing a year, and then you see them again, right? So in that case, you don't know what happened in the missing year, right? And so then you normally have to allow for all the possible things that they might have chosen in that year. You know, maybe they chose working or they didn't choose working, like you don't have that data. And so then you have to add up the likelihoods for all the different things it could be, right, for the years that are missing.
So that's not too nasty in this problem, because we just have two choices. So when you're working on more complicated problems, do you, I mean, maybe in the end you like to do that whole thing, but do you like begin with like you select on a balanced sample where everyone has the same number of, well, because it doesn't have to be balanced, but it has the same number of, it's complete within the...
Yeah, missing data is kind of a headache for maximum likelihood approaches. And so usually, if I had a lot of missing data, or sometimes the sampling even is like every 5 years, or you know, then they don't even sample people. Then people sometimes choose instead to do method of simulated moments instead of, so there are different estimation approaches. I mean, I usually prefer maximum likelihood because this method uses all the information, it's efficient, it's not arbitrary. The moments that you're actually using are the first order conditions from the likelihood, right? So if you want to translate this to a method of moments, maximum likelihood, the first order conditions, those are your moments, right? Simulated, well, method of simulated moments is like GMM, but just a simulated version of GMM. There you have to decide what moments you want to use. And that method is easier with missing data, because you don't have to like integrate out over the missings, which you're doing when you add up the likelihood for all the options it could be. But it's got some arbitrariness about what moments you specify. It's hard to see what's identified, like if the moments that you picked are enough to identify all the parameters, you know, so, but the reason sometimes people choose that method instead of maximum likelihood is because of missing data. Because it's not that easy to deal with lots of missing variables. So one option, you just throw them out, you don't use them. I mean, that's definitely an option that you might want to go with. Okay, so in this example, we have this additive error, but that's actually not required. You know, so it just made it a little easier to get these expressions. But in general, you don't have to have additive errors. Okay, so given joint normality, you can actually, this is putting in what those probabilities are. It's just writing. It's just writing in explicitly what the probabilities are. So you actually have, in this example, it's simple enough that you can actually just write out what this expression is. Usually the models aren't that simple, and so a lot of the stuff I work on, you have to solve through simulation methods. So we'll look at like how you do it. If you have more shocks, then it's not as simple. But in this example, it's pretty simple. And when you're estimating these models, you have to iterate between the solution of the dynamic programming problem and the likelihood. So the way it works is, like, you're searching over the parameter space, right? So you start with some guess, you solve the dynamic programming problem for that guess. Then once you get these Emaxes and the cutoffs, then you write down the likelihood, and then you go to a new guess. So you use some sort of optimizer, like simplex method. Some of the models, a lot of these models are not, they have discrete choices, and a lot of times they have jumps in them, so they're not differentiable. So usually you have to use optimizers that allow for non-differentiable functions, like simplex method would be one method. But you just iterate between solving the dynamic programming problem, specifying the likelihood, and then going for different sets of parameters, searching over the parameter space. And then once you estimated getting standard errors and everything is completely standard. It's just the usual formulas for maximum likelihood standard errors. So the only additional thing is the discount factor. That was the one new variable. And I mean, the main complexity is computational, really. It's just having to solve this dynamic programming problem along the way in order to get the likelihood. So it's just, you need powerful computers usually to estimate these dynamic discrete choice models. Okay, and we have the same requirements about exclusion restrictions, so that's not different. In this model, work experience could serve the role of an exclusion restriction, if it doesn't directly enter into kappa. Okay, and the discount factor, just to make sure that it's identified. So this is the latent variable we have. So we have this linear stuff, and then we've got, this is the difference in the future components, right? The expected value functions. This is also a function of the same state space elements, right? This observable state space is this. These are the same variables. But we have these nonlinearities, so given the nonlinearities and the function form assumptions that we have, that's sufficient to identify this discount factor. But it is true that this part is a function of the same variables as this part. So we are using the function form assumptions for identification.
Is that going to give you like a reasonable discount factor usually? Or I just have in my head that macro guys have a really hard time getting discount factors that are like close to 1.
Yeah, if you don't have a lot of data, a lot of times people will just assume a discount factor, 0.95 or something, because it's difficult to estimate it if you don't have a pretty long panel. Yeah, that's true.
For the exclusion restriction, so is it usually kind of hard finding a good exclusion restriction? So in the sample you gave earlier, where you're looking at women in, say, their 30s, I think usually around that time we can kind of think of the profile of wages and experience and be a bit flat. So does that give it, something like experience really giving you enough variation to essentially identify that?
I mean, it is hard, I think, to come up with good exclusion restrictions. Yeah, you need something that affects the wage offers.
What are common ones? Are there common ones?
Yeah, I've used some things in my work, like, well, when I had to do a wage offer equation, I used a distance to the city, like how far away they lived from the city, because that affected their earnings opportunities. So like features of the environment. So it is challenging. I mean, it's a little like coming up with instrumental variables. Right. It's pretty close. But you do want to have things that independently vary certain elements in your model. You want everything to just be dependent on the same sort. Some models can be estimated without exclusion restrictions. But even then, then you rely heavily on functional form to separate out the different things. So people will like your work more if you have some independent variation in these different parts of your model. So or something like regionally, something about the environment that they live in that might affect their, it's complicated though, because you can't really put things like the local unemployment rate, you know, you might think that you could put things like that in there, but in these models, you actually have to take a stand on how people forecast all the things that are changing. You know? So anything about the environment that's changing, you know, people would have to have some forecast over how it's changing, because that would already affect their decision today.
I mean, and unemployment's not actually in the model. There is no.
Yeah, and unemployment is a weird thing, because if you aggregate up everybody's decisions, you know, yeah, first of all, it's a model where people are choosing whether to work, so it's voluntary unemployment. So.
You wouldn't just like assume some kind of rational expectations in figuring out how they forecast?
Yeah, you'd have to have that as an additional ingredient in the model, like some sort of forecasting equation of how they forecast different elements.
So Petra, to pursue that, I mean, in rational expectations econometrics, the typical procedure is you construct something that is a forecast error, and that immediately gives you all the instruments, or at least it gives you orthogonality conditions, because then you just say these are all the information set of the agents, and hence are uncorrelated. There isn't a trick like that that you can use.
No. I mean, the ones where they assume rational expectations, usually those are like general equilibrium versions of these models, where you have all the individual decisions and you aggregate them up. I mean, a lot of the recent work, you know, a lot of the general equilibrium modeling, they don't try to estimate the micro model like this, right? Or they might just calibrate it, because it's very complicated to estimate. But there is some recent work on estimating these models and then aggregating up the decisions to get the aggregate quantities, you know, and then imposing general equilibrium conditions, you know, along with the model in estimation. And there you actually would have forecast equations that specify how people are forecasting the future, and that's where you would impose like rational expectations. So that's just, there are not tons of papers that do that. I mean, it's pretty recent work. Like Heckman, Lochner, and Tabor actually, I don't know if they'll talk about it, he might talk about that this afternoon, but they are one of the first papers where they tried to do something like that, and then Wolpin and Lee have a paper, and then there's another paper by Lee. And just recently, like on the job market, we've seen a few papers like doing that type of work. Aggregating up the decision and imposing like general equilibrium conditions along with these models.
So what would be the alternative like specifications for forecasting if you didn't assume rational expectations? I mean, I myself have never estimated this type of model, so I think that it's not that easy to assume rational expectations. Or the forecasting equation, usually they have to have some approximation to the rational expectations, and then there's some debate about whether it's a good approximation or whether they put in the right variables, or so I think it's not even that easy to impose the rational expectations.
Especially because if you observe in the data that people aren't doing a great job at that, right?
But how do you observe that in the data? Like,
Well, if you're going to observe that, then that makes it falsifiable, so you can assume it.
There has been some attempt to incorporate if people are ignorant about certain aspects. Like, suppose there's like a production function in the model, like in the child investment models that deal with child investment. People may not know the technology for converting inputs into outputs, and so people may have different ideas of what the technology is, and they may be biased. Like they may think that something is not effective in improving child outcomes. Like they may not know that reading to your children causes them to have better reading ability. So they may just not know. And so you could incorporate into these models that they're ignorant, or some fraction of the population is ignorant about this, you know? Or people have tried to incorporate like hyperbolic discounting into these models, like present-orientedness. And so there have been some attempts to not just have rational expectations. But otherwise, these models are kind of hyper-rational because people are, taking account the future. And,
right.
Yeah.
Yeah, and I guess I just have in mind the industry dynamics literature in IO, where if you're assuming that everything's evolving according to, you know, equilibrium strategies, and therefore, you know, people are correctly predicting the future, and if you've got a set of data over time, you can just extract their beliefs directly from the data, and then recover everything else conditional on those beliefs that you now have in hand. Would you use that kind of a strategy here?
I'm trying to think what the analogy would be here. I mean, these are like single agent.
Oh, okay.
And I owe multiple agent models.
Okay, right.
Isn't there a stream of this literature, and I think I took Peter Arcidiacono's class, and isn't there a stream of this literature where you're just actually doing a 1 period or 2 period because of there's some sort of like finite dependence on the past and the future. So like in that case, you don't have to actually rationally think of everything from here to infinity. You just are thinking of 1 period ahead.
I mean, there's some estimation approaches where you do 1 period ahead, or you could put like Markov structures on some of the elements of the model.
Yeah, and that only really requires you to be rational 1 period ahead.
Okay, I think you're probably thinking about the Hutz-Miller. Yeah, I have some alternative estimation approaches, some slides about. There are some different methods that don't require you to solve the whole model.
And it also requires you not to be rational for ever in the future is part of that, I think.
That's normally the model's the same. It's just an easier way of estimating it. Like where you don't have to, I mean, you could specify your model up to whatever period you want. Like you could just specify up to time t, whatever the t you want. And sometimes people incorporate like terminal value functions, you know, at the end instead of like here at 0. But, okay, so one important thing in these models, like if you introduce, say, a subsidy experiment, the effect of a subsidy, like a childcare subsidy, will differ in this model, like in a dynamic model, than in a static model. Because here, people also will take into account that if they work, you know, that'll affect their work experience and that'll affect their future wage offers, right? So if we estimated a static model and a dynamic model, you would get a different effect, different policy effect. And then the other thing that's important in dynamic models is when you introduce the subsidy, you have to tell people, was this a surprise? You know, because if people are told about a policy in advance, so if people know that a subsidy is coming next year, in a dynamic model, this will already affect their behavior potentially as soon as they hear about it, because they're taking into account their future, right? So they may say, oh, next year there's going to be a child care subsidy, so why don't I not work this year, because it'll be cheaper next year, you know? So if they know about the policy versus not knowing, you could get a different effect. So any pre-announcement, you have to take into account when was it announced. And then you also, if you had a pre-announced subsidy, you would have to solve the dynamic programming problem back to the period of the announcement. You know, because the whole solution would be different with the subsidy versus without. So you would solve the dynamic, I mean, first of all, in your data, there's no subsidy. So you estimate all your parameters with no subsidy, right? Because that's how the data was. But then if you want to say, well, what would be effect of a subsidy that was announced 5 periods in advance? Then you'd have to resolve the dynamic programming problem. But you have the parameters, so you don't have to estimate the parameters, but you do have to resolve the Emaxes. And then you'd have to use those Emaxes for doing the policy simulation with the subsidy. So these are like, you know, whenever you have any sort of policy, you have to say, when was it announced? Was it a surprise? You know, when did people start taking it into account? Okay. So there is a lot of literature trying to make the solution of these models a little bit simpler. And so not a lot of people have seen John Russ work on this. And he shows that when the shocks come from type 1 extreme value distributions, then you can actually get a simpler expression. So again, it doesn't look simple, but the simpler part is that there's no integral. Like in the normal CDF, you have these integrals you have to solve numerically. So this result, all of this is really meaning is, you know the old results about if you have a logit model, that if you have Weibull errors, the difference between two Weibulls is a logit. Like when you do just McFadden's results on like multinomial logit models and how you estimate. Well, whenever you do a logit model for two choices, you're assuming that the errors are like type 1 extreme value, because the difference between two type 1 extreme values gives you the logit. And essentially that's what John Rust is also doing here. He's just saying the difference in those two errors gives you logistic. And that's true if the errors are type 1 extreme value. Okay, and so under that case, then the probability that you work has this, well here that you don't work, has this expression. And that's just the expression for logit CDF. Right? E to the x over 1 plus e to x.
And this is useful just because it means that we don't have to compute numerical
intervals. Right.
Okay, and that's
yeah,
it.
that's the main usefulness. Well, you'll see there's another method that the Hutz-Miller method uses this expression. But this is useful for that, and so you get these closed form expressions for the Emaxes. Right.
Are the results typically very different depending on the method, or?
You know, there are not a lot of papers that use different methods. Like there's one paper by Steinbrückner that tries out different methods, but there are a whole bunch of different methods in literature that people adopt, and they don't usually do multiple methods, so it's hard to tell.
I'm just thinking about comparing the normality assumption to the extreme value type 1 assumption.
Yeah. I mean, normally, like for binary case, it doesn't make a big difference, but for like more than two choices, I think it can make a difference. But there isn't a lot of work. I mean, there's work for static models. Like there's some older work by like Hausman and Wise, I think, where they compared, and it did make a big difference. And that's when they try to develop like nested logit models and things. But in these types of dynamic framework, I haven't seen a lot of papers comparing different assumptions. Okay.
So you assume the T1 UV distribution at the cost that you have to assume the additive errors.
Yes, exactly. That is a cost, the additive error structure. And I think that's a pretty severe cost, actually, in a lot of applications. Because even in this application, additive error is not really reasonable because you'd want to have log wages. You don't really want to have a wage equation. You want to, usually log wages, we assume log wages are normal. Wages themselves don't look normal. They have kind of more of a Pareto shape. So, so that's a pretty severe restriction. Yeah, and it's not really necessary. Like some people seem to have the impression that it's necessary even to estimate these models, to assume these error structures. That's not true. Like you can put the error wherever you want. You can put it like, e to the epsilon or anywhere you want to put it. It doesn't even have to be in the utility function. So through simulation you can solve any sort of structure you want. It's just you don't get the simplification and you have to solve numerical intervals. Okay, but this is kind of a popular method just because it has simple expressions. So it depends on how severe a restriction that is. So this is just writing out what the Emax expressions are. And it is amazing that this is the simple method. But, let's see. So, and the solution is otherwise the same. Like you still have to solve the Emax function. So the only difference is they now have a closed form. And also the choice probabilities have a closed form. So there's no simulation required. Okay. And this is just saying that's kind of problematic because wages, you would normally want log wages. So even in this example, how could you fix it up? Like you say, you didn't want to have to assume wages had a normal shock. Well, there are a couple ways you could fix it up. You could say the wage offer is not observed at the time participation decisions are made, so that the wage offer doesn't affect your decision. Or you could say, so that's and the other thing you could say is that it's all measurement error. So in your data, yes, the two women that look identical made different decisions or whatever, but you could say that their wage was actually identical. It's just not identical in your data because they had different measurement error. You know, so there are ways of kind of shoving it into the Rust framework, even though without having to make the normality assumption on wages directly. So this is something that's often assumed, that some of the errors are measurement error. It makes it a little easier because then people aren't actually using those errors in making the decision. And then you just can incorporate it directly into likelihood. Okay. Yeah, so this is just saying, so because then you'd only have one shock that was affecting the utility, and then that could be type 1. Well, then you'd, I guess, have to assume that that was logit directly, because you wouldn't have the difference anymore. But whether the model assumption is necessary to take advantage of computational gains, like whether you want to do that, you know, it really depends on what model you're estimating. You know, whether this additivity assumption in type 1 extreme value is reasonable. Okay, now unobserved state variables. You know, you may have not liked the assumption that the errors were serially uncorrelated. You know, like for wage shocks, for sure, you know, wages are highly correlated. You know, it's usually not a good assumption to assume that shocks are totally just uncorrelated over time. And that assumption can be relaxed. Normally, the way people do this is using this idea that first came from Heckman and Singer in 1981. And so if you know this work, do you remember this paper? Do they still teach Heckman and Singer? This was a famous paper when I was in grad school. This paper on duration models, where they introduced permanent unobserved heterogeneity in the duration model in the form of discrete types, right? That people, and it's kind of analogous to fixed effect assumption. It's saying that there are these fixed types in the population. So with fixed effect, everybody gets to be their own type, you know, because everybody has their own fixed effect. In these models, it would be too hard to allow everybody to be their own type. So we usually choose a lower dimensional number of types. Like you could say there are 2 types in the population or 5 types in the population. And then we say that the error structure has this form. So there's some type, permanent type, and then there's some ID component. So because we had a model of households, you could think about there being a type for the husband and a type for the wife. You know, and you could restrict them to be the same type if you wanted to, you know. And then this would be the type for the woman. But it's basically like a fixed effect error structure, the permanent component plus a random ID component, right? And Keane and Wolpin were the first to use this in a dynamic discrete choice model. But the idea is very similar to the Heckman-Singer idea for duration model. Okay, and it's assumed then that the couples know their type, or their spouse's type, and so that now becomes part of their state space, their unobserved type. We don't know their type, so it's for us it's kind of like the unobserved shock. And when you estimate these models, you now have to solve the dynamic programming problem for each type. But then the likelihood you integrate out over the types. So these are the different types for the woman, the different types for the man, and then you estimate along with the model a type probability function. Like the probability of being a certain type or a certain combination of types. Yeah, so these are some like auxiliary parameters that have to be estimated along with the model, but the benefit is you're now allowing for permanent unobserved heterogeneity, that people can differ permanently in unobserved ways, like unobserved ability, affecting wages. There are many reasons why we think unobserved health endowments. There are many things that we might consider endowments that you want to allow for, like permanent unobservables. So nowadays, if you estimate these models and you don't have types, people will probably complain that it doesn't allow for permanent unobserved heterogeneity. Okay, the only complication is just computational because now we have to estimate the dynamic programming problem for each type in your population.
In a few minutes, can we take a 15-minute break?
Yeah, I forgot what time is our break. Are we already over?
A little bit.
We started a little late, so I would just propose we break when you think there's a natural spot, and then we reconvene at 11.
Okay, I think we're pretty close to a natural spot to break. So, an alternative assumption to the types, right? So types is one way to introduce permanence, because now the wage shocks are correlated over time. It's not just by ID. And actually, these models fit the data a lot better when you have some permanence in them. Because otherwise, you'll see people bouncing in and out of working and not working way more than they do in the data. Because in the data, people are pretty permanent in the decisions they make. So if you don't allow for that permanence, it's hard to fit the data a lot of times. An alternative assumption would be that the shocks are serially correlated, right? Like an AR1 error structure. Which intuitively is fine and, is very nice. The only complication is that this introduces the lag shocks into the state space, right? And so then, instead of just having discrete variables like, how old the person is and what their education level is, now we have these continuous variables, which are these lag shocks. And so continuous state space elements introduces just some computational complexity that we have to deal with. Because now you can't solve, remember the cutoffs you had to solve for all the different state space elements. Well, if it's continuous, you can't do it at all the different state space elements. And so that's why we then have to introduce some approximation methods. So you can do this if you want to, but then you have to use some methods to account for the continuous elements in the state space. All right, so...
Can I ask a question about the previous slide? The identification of the type probabilities, is that coming off of the nonlinearities and the likelihood? Or how are we identifying those in the data?
Yeah, normally if you specify these, I would specify them as a function of the initial conditions of the model when the model starts. Yeah, it's definitely functional form because this likelihood is all parametric. And this is functions of the same stuff that might enter the type probability. People specify in different ways. Like when I do this, I normally would do like a logit, like a multinomial specification for the type probabilities, if I have 5 types or something. And then usually you would put what are called the initial conditions, like whatever started at the first time period, and that would be the type probability. So whenever you start seeing the people, that's what would enter into this. And it is the same as this. So if you're parametric here, sometimes you can be non-parametric here, because you're parametric here. But it is the same elements are entering the 2 parts. So you want a break? Is it 15-minute break or half-hour break?
It's 2:11, so
2:11, okay.
but it's martial law.
Yeah, all right, so we'll be back at 11.
Thank you.